All right, people joining us, we're grading 8.4. Pause me if I'm going too fast. We already went through the beginning answers. My microphone just died and needed new batteries. So there's number 6, number 16, number 44, solving it both ways. Got to 64, 56. We love zeros. Here we go, 62. This is the one you guys were talking about, right? Yeah. Woo, 5 by 5. Unless you go along the diagonal. Because if you did column 1, you have a 5. And then this big old huge, oh wait, but then you have a 1. And this big old huge, oh wait, but then you can, well, I guess you could have gone. But why not go to row 3 where it was 0, 0, 2? So then you had a positive 5 times the next one, times a positive 1, times, because all the rest are 0, times, well that's positive, negative, positive, positive, negative, positive. You just have your 2. So positive 5 times positive 1 times positive 2, and what was left? 2 and 6 and 3 and 4, main 8 minus opposite 18. 8 minus 18 is negative 10. 2 times negative 10 is negative 20 times 5 is negative 100. But it takes some time for you to be able to do that mental math style. But it wasn't as bad as you probably thought looking at it at the beginning. And then 86 is the one we just talked about, or something very similar, I should say. Distributing, combining, factoring, dun, 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 dun. All right, what do we got? Any further clarification necessary? Odds or evens? Going once.
Oh,
got it.
35.
Okay, anything else besides 35? Oh wait, I'm totally in the wrong section. This is 8.5, what we're supposed to be doing today. I was like, what? Lo Santo. What was it, Jason? Number 30? 35. Was he not working out for you? All right, Jason, this is the right problem, right? Jason, is this the right problem?
Yes.
Cool. You guys tell me. They didn't tell you. You got to choose what row, what column.
Row 1.
Has a 0 in it, right? Does it make sense why I'm doing a positive 4? Okay. And then I'm going to do 0. Technically, it would have been a minus 0, to be honest. So I don't even need to worry about it's 2 by 2 because it's 0. And then plus 2 times. So for 4, I have 2, 1, negative 1, 1. And for 2, I have negative 3, 2, 1, negative 1. I have main, which is 2 minus opposite, minus a negative 1. It's 3. That's just 0. Plus 2. Main is 3. 3 minus 2 is 1. I think, bud, you should have gotten 10.
So that's the determinant. You're finding cofactors.
Oh, see, I didn't read the directions. Struggle. Okay. But wait. Okay, so we have some cofactors right here, right? Cofactors are the sign put together with the leftover, right? Because that's the entry. The minor is just this guy. The cofactor is this guy with the sign. And where was the 4 at? What spot was he in? The 1, 1 spot? So wouldn't C1, 1 be the positive determinant of 2, 1, negative 1, 1? Which would be main 2 minus opposite minus negative 1. So that'd be 3. Are we supposed to find all the cofactors, though?
Yes.
So then going to 2, I mean, I didn't have to consider 1, 2 because it was 0. But if I had been considering, remember, I said it would have been a minus. Then we would have taken who was left, which would have been negative 3, 1, 1, 1. So that'd be a negative. Main minus opposite. Negative 3 minus 1 is negative 4. Minus a negative would be a positive 4. Is that okay so far? So then you guys tell me, what's my cofactor for 1, 3? It's also kind of shown up here. But we don't use the entry, not for cofactor. We use the sign, and we use the leftover. The entry is us actually doing the determinant. The formula is A11 times cofactor 1, 1. And A12 times cofactor 1, 2. And then A13 times cofactor 1, 3. So what's everything besides the whole little 2 part?
1.
Yeah. Because it's positive, what you would have had left. 3 minus 2. Is that cool? So then to finish, you would have done the exact same procedure, ignoring the entries, but thinking about what sign, positive, negative, just to do one last one. Positive, negative is in the 2, 1 spot, but not the -3, just negative with the sign. And then Jason, what's your leftover minor? What's your 2 by 2 for that spot?
0, 2, -1, 1.
You got it, kid. And as soon as you have that, all you have to do is do main 0 minus opposite minus -2 is positive 2 times a negative. There you go. So then keep going. 2, 2, 2, 3. 3, 1, 3, 2, 3, 3. Minors are before the sign.
Oh, I see.
So this is the minor of just 3. Cofactor said positive 3. It already was, but that's okay. Minor said -4. Cofactor said positive 4. Minor said 1. Cofactor said, sure, 1. Is that cool? Okay. Good question, though. Yeah, it got a little funny when they started asking for not the whole thing, but just parts of it. Anything else from homework? This whole matrix thing, how we doing, guys? Oh, 86? That was our last one, right? So Lauren, remember when there's one like little baby step they didn't show, so let me come right here. One jump they made. Those little absolute value mean determinant. So we had to do our main, those two multiplied together, minus our opposite, and then you would have gotten x squared minus 2x. Oh, I guess actually they did do it. That would be a positive 3, but then we have a negative or a subtraction, so subtracting a positive 3 is minus 3. Now we just have a quadratic, so we just go back to algebra and say, well, how would we always solve this? We've done the determinant to get our problem, now we have to solve our problem. So that's why they went to factoring. And getting -3, positive 1, we have an x and an x. Set each one equal to 0. But it had to start with main minus opposite because of those absolute values. Anything else? Odds, evens? Going once. Going twice. Sold. 8.5. Guys, get your calculators out. All chapter I've been saying, yes, we need to learn how to do things by hand, but yes, sometimes the calculator will be allowed. This section, we're going to be using our calculator. We're going to have to be able to do some things by hand. But we're also going to make sure that we can use our calculator as well. So grab out your calculator. If I were you, I would actually go clear out all of your matrix things, your A's and your B's. I would clear out your matrix things, your A's and your B's. Yeah. Okay. Guys, check out the title of section 8.5. What do we have? No, the title. Applications. So this is the section that's basically like, hey, let's use it lots of different ways. Yeah. Okay. So we're not learning anything new as far as the matrices themselves, but we're learning how to use them. The first big thing that we're going to learn is Cramer's rule. Cramer's rule is a variation on solving a system. Cramer's rule is a variation on solving a system. Wait a minute, hold on. Do you guys see the formula for Cramer's rule? The formulas look really complicated. But wait, don't you kind of see mains and opposites? And mains and opposites? But hold on, these are weird matrices because C is going with B. C1 is going with B2, but it's going backwards. And C2 is going with B1, but backwards. That's awkward and weird. Unless you realize, well, this could have come from a main minus opposite if it was written like this. And this one would have been weird too. A1 goes with C2 and A2 goes with C1. It's awkward. Why is it skipping the B's? But it could be a determinant, a normal determinant if you write it like this. So even though these aren't bad to know or to memorize, I would say this is a lot easier. We just need to figure out why did the matrices get written in really weird ways. Now the denominators should be kind of normal because it's like, oh, A1, B2, B1, B, A2. They wrote it in weird orders, but it's main minus opposite of just this guy. So both denominators are just looking at the matrices, the determinant of the matrices formed by the coefficients. Boom, boom. The numerators, though, how on earth would we have gotten these numerators? There's a pattern, and the pattern's going to be helpful. There's a pattern, and the pattern's going to be helpful. Now, guys, on the test, technically, you'll probably be able to plug this into your calculator to solve, but to get full credit on this multiple choice Cramer's rule question, you'll have to write out the formula for it. Then you can go to your calculator, so be careful. Yes, you're going to be able to use your calculator because, as you can tell, there are lots of determinants. However, to use your calculator, to get full credit, you're going to have to write out the formula. So what happened? Guys, what column are the x's in up here at the very beginning? What column? What column are the x's? The first column, right? The A1, A2. What do you see missing from the numerator? So to find x, we ignore his entries. See it? To find x, we ignore A1, A2. And what's in the spot of A1, A2? The C's came in. Okay, let's see if that pattern works over here. What column are the Y's in? The second column. What letters do you see that are missing? The B's from the second column. Who's in the spot? C's. There's a pattern to Cramer's rule. Cramer's rule says that we can solve a system of equations using the coefficients, well, using all the numbers from the system set up in matrices, but we make little fractions where the denominator is always the determinant of the coefficients, and the numerator is the determinants, or are the determinants, is the determinant, sorry, of the matrix formed by ignoring the coefficients of the variable you're solving for and bring the solution in. So, there is this whole little formula for it. I don't really like that because it just makes it more complicated than it has to be. If I was to give you something like this, it's an actual system. To get the correct answer on the test, could you use substitution? Ugh, this would be a nasty substitution problem. Could you use elimination? Yeah. Could you use RREF? Yeah. But if I say use Cramer's rule, remember, I'm looking for what? You to write out the formula, and then you can use your calculator. Bless you. You guys realize we're missing x and we're missing y, right? For both of these fractions, from what you wrote down yesterday, and we revisited just now, both denominators look at the determinants of just the coefficients, 4, 3, -2, -5. So one way to start Cramer's rule is to do the determinant of just the x's and y's, which, main minus opposite, would be -20 minus -6. -20 plus 6 is -14. From one little baby determinant, I have half of each of my solutions without doing substitution, elimination, RREF. Now, if it was a bigger system, it would be harder. If it was a bigger system, it would be harder. But a little 2x2 is not too bad. Now, I want you guys to take a second in your groups and try to form for me what matrices I'm looking at for the numerators. The denominators were the same. Both of them used just the determinant of these 4 entries. But I want you to try to make the matrices. You don't have to solve them yet. Use the formula and try to make the matrices that we need, that would find the numerators of the solutions. Ready, set, go. You're allowed to collaborate. Try to use the formulas. you think you have them and your group agrees with you, go ahead and solve them then. If you think you have them and your group agrees with you, go ahead and solve them then. All right, let's see if I agree with you guys. Did you guys think about, in order to get the x's numerator, you had to look here, ignore the x's variables, and bring in the c's. So it would have been 10, 11, -2, -5. To get the y's, who do you ignore?
The Y's.
The y's, and what do you bring in their spot? So 4, 3, 10, and 11. Now we solve. And we say, okay. So x is equal to, main is -50 minus opposite. -50 plus 22 is -28. Hey, that ended up being nice. X equals 2. This one, y equals 44 minus 30, is 14 over -14. Y equals -1. Now, with how nice those numbers are, do you think this might have been easier just with substitution? Elimination, maybe?
Yeah.
Okay, with how those numbers are. Based on you guys understanding what just happened, pause. Anybody want to ask clarification on anything? I'm going to give you another system that might not have been easier with elimination. But some of you are like, I think elimination would have been easier. Can you guys try to solve this one with elimination? Unless you're like, I think she's setting us up for trouble. Unless you want to go for Cramer's rule again. I'm going to go Cramer's rule. But on my little baby whiteboard up here, I did elimination. And so we can compare. So if you don't believe me, if you're like, no, elimination, psh, forget Cramer's rule. Okay, go for it. But if you're listening to me and you're like, I think she's setting us up for trouble, maybe you'll try Cramer's rule like me. And you'll believe me when I show you my whiteboard of work for elimination. Ready, set, go. Yeah, thanks, Matt. You want to see my elimination work?
Oh.
Guess what I would have had to do? Multiply, I multiplied this guy by 5 and that guy by 3. And I was like, all right, stuff canceled out. And pretty quickly I got 13 over 47 for x, which is right?
Mm-hmm.
But the dilemma is, you would have to take 7 and do what to get y?
Plug it back in.
Back substitute. I have to plug in 13 over 47? Mm-hmm. Or I have to plug in 1347? Mm-hmm. And solve. Now, is that impossible? No. But would it have been nice? How hard were these numbers?
Easy.
Not bad. So could Cramer's rule be a faster variation on solving nasty two-variable systems? Yeah. Now, if this was a 3 by 3, okay, well, would solving a 3 by 3 over a 3 by 3 and a 3 by, would that have really been easier than just RREF? I don't know about 3 by 3s, but 2 by 2s is kind of nice. And having a computer program do Cramer's rule might even be faster than RREF as far as programming. Anyway, that's one option. I don't want you guys to actually solve this by hand. I would have you use a calculator for this, but I'm just curious if you guys, based on what we've done, could tell me how to set up x and y and z. Is that okay? Now, x and y and z would all share what?
Denominator.
Okay, and how would you find that denominator? And let's just call that d for denominator. Is that cool? Plug it into your calculator, solve, and then wouldn't that be all of their denominators? But what would you have to do next? Okay, so just tell me what the numerators would have been. What would his matrix have been? Good. You would plug that in, ignoring the, do we get the pattern? Whatever size matrix it is. Just take out that column and put in the solution column. So what would be the rest of your matrix? Got it. For y's, who are you taking out? Not him, right? But what goes next? What's my next column? There you go. We take out the y's and we put in the solutions, and then you have your 1, -2, 1. And then what would this guy be? Then bring in. There you go. So could you guys find him, have all your denominators, and find the determinant of for each of your numerators? Yeah. So Cramer's rule works for, oops. There you go. Works for any system of any size. Is that okay, guys? Just the general gist of Cramer's rule? Okay. Nah. Well, you guys would be awesome if you did. To be honest, in this one though, Jason, if I had my choice, like I would, if the question told me use Cramer's rule, I would write this down. But doesn't that sound like an awful lot of plug and chug into your calculator? Yeah. I'm going to be honest. I would put this in and do RREF and be like, that's the answer. But I would write my Cramer's rule to show that I knew how to do it. Does that make sense? Because RREF, wouldn't it get to 1s and then be like 1x, 1y, 1z with one matrix instead of with 4? Because you have to do a denominator and 3 numerators. That's just me being lazy. The next application. There's actually 2 applications in one. It has to do with area and collinear. Area and collinear. Kiddos, what's true about any 3 points? What shape can you make with any 3 points? Right? A line needs 2 points. So is that true? Any 3 points, it's a triangle?
Yeah.
Any points? How about any 3 points? Whoo! So the only time 3 points won't make a triangle is when they're all on the same line or have the same slope between them. Yeah. Any 3 points can make a triangle unless they're all on the same line. If I can draw a triangle between any 3 points, what does that mean about area? Area, right? Has an area, right? Has an area, right? How about this one? No area. Huh. Okay, anyway, we'll come back to that in just 1 second. But let's talk about area. So if you have any 3 points that aren't collinear, it's going to have an area. And here's the cool thing about area. If I was to give you guys, like the example on the next page, I was to say, hey, you have the point 10, the point 22, and the point 43. Find the area. You You could do distance formula and distance formula and distance formula, but even when you have three sides, wouldn't you have to go back to that law of sines, law of cosines chapter and go back to Heron's formula and do the square root of s times s minus a times s minus b times s minus c to find the area with the a, b, and c? So 3 distance formulas and Heron's formula. 4. You do one point, you do another point, you do another point. Doesn't matter the order in any way, shape, or form. You make it a square matrix by adding a column of 1s. You take the determinant and multiply it by a half. If it's positive, you make it positive. If it's negative, you say, oops, it should have been a negative. Long story short, you just say area always has to be positive. So whatever sign it ends up with, think absolute value. But we can't put absolute value around it because in matrices it doesn't mean what it means with numbers. So they put this little plus minus thing. But long story short, just make it positive. So the cool thing is you guys are allowed to use your calculator. You put a 1/2 and you put these in any order. 1, 0, 2, 2, 4, 3. You add a third column of 1s. Can someone get this in their calculator? Use the DET option. Then divide by 2 or multiply by a half. I just need to know what the number is and what the sign is that naturally occurs. But do you see how easy that was? 1 point, 1 point, 1 point, 1, 1, 1, 1/2. Calculator. If you had to do the determinant by hand, I don't know about you guys, but it sounds a lot better than distance formula, distance formula, distance formula, 3 numbers, Heron's formula. Both are possible. This one sounds nicer. When you give me the answer, make sure you've divided by 2 or multiplied by a half the determinant. Is everybody okay? Is everybody okay with using their calculator? Now guys, can area be negative? But I can't put absolute value around that. So what would the formula tell me to do? Choose the negative to multiply, and the negative times a negative. The long story short is just always make your answer a positive with area. Long story short, always make your answer a positive. So if it's a negative, no big deal, times the negative. If it was positive, cool, I would have chosen times a positive. But long story short, the formula always gets you the number, the numeric value, just make it a positive and you're done. That's kind of cool. But then the question comes out of what I just showed you on the board. So will this area formula ever fail? The answer is no. It'll never fail, but the weird thing that can happen is sometimes you can have the area formula, the determinant, give you a 0. And what would be true if the area formula gave you a 0? They're on the same line. So the area formula will always get you the area of the triangle formed by 3 points, but the weird thing that'll happen is every now and then you might get the area formula equaling 0. Well, wait a minute. Will the 1/2 times, will the 1/2 ever get you 0? No, 1/2 times never get 0, but what could get 0? Well, I was just thinking the determinant. Like the 1/2 doesn't make it 0. The determinant could make it 0. So they've just kind of narrowed it down and said if the area is ever 0, well, it's because the determinant is 0. Ooh, the inverse doesn't exist. It's a singular matrix. There are lots of ways of describing a matrix whose determinant is 0. But in application, when talking about collinear points, we're talking about triangles. If the determinant is ever 0 when making this special formula, that meant that they were all on the same line. There is no triangle that can be formed. So guys, let me go ahead and, my hair's stuck in my microphone. Not that you guys needed to know that, sorry. My question, are those collinear? Yes or no? First use the matrix idea, and then after you use the matrix idea, okay, maybe you can start thinking about it a different way, being like, oh, maybe I could have found this out another way. But the question is, are these collinear? The question is, are these collinear? Use the matrix way. Just find the determinant. of all 3 points with a 1 in the final column. Is it 0 or is it not? Then think about how else could you have figured this out? Maybe there's more than one way to figure this out, but I'm asking you to try the determinant. Is the determinant 0 or is it not? And I'm going to do it too. It's a 3 by 3, right, guys? What's the answer?
3.
Did I put it in my calculator wrong? I got -6. Oh, double check.
Oh, so I got 6.
Oh. Jason was actually doing the whole area. But long story short, yeah, there is an area. The area would have been 3. You're totally right, Jason. I'm just saying there is a determinant. So just an answer to this question, is it collinear? The answer is no, because as Jason said, you can find the area. The area would be 3. But the reason I can say no even quicker is the determinant's not 0. So there is a triangle. There is area. Ironically, it doesn't look like there's that much area, but there is quite a bit. That's a horrible triangle. But anyway, not in the same line. However, I did ask you guys to ponder, was there another way of doing this? Did anybody figure out the slope, the rise over the run to that point? You had to go up 3 and over. Oh, I thought it was 4, but my line went too long. It is up 3 over 3. M is 1. So this line would be a 1x plus, has a nasty intercept. Or maybe it doesn't. But anyway, I can make an equation of this line and it would have a 1x. But what happens if I go from this one to that one? I'd have to go from 1 to 5, which is 4, rise over run, and from 1 to 7 is 6. Is a slope of 1 and a slope of 2/3 the same line? Nope. So there was more than one way to answer the question, but one way with determinants is, hey, determinant 0, they're collinear. Determinant's not 0, they're not. This is a nasty type of question that you guys might see in homework. We'll talk about the answer on Monday if you guys aren't able to use the book examples, how to find an equation of the line passing through the points using determinants, but let me at least show you the setup, okay? If they're all on the same line, determinant is 0. And if they're all on the same line, well, this point and this point and a general point would all have to work. I wonder if there's a way to find a determinant when there are variables inside. Okay, last application. This is like a quick little homework help and like, how would you keep going? But the last part of homework. Kind of. You can technically take a picture of the letters if you want. But basically, do you guys see the pattern to the letters? Let me move this down so that you guys can see. Cryptography. Cryptograms. Ciphers? Deciphers? Coded messages? There is one last application of matrices, and it's a way of mixing up a message. Now, a way of encoding a message from letters to numbers, that's been around for a long time. Giving letters numeric values. I took a class in college about cryptography. That was kind of fun. It was a math elective. Encoding messages with numbers, that's been around for a long time. However, if I was to give you a piece of paper that said 8, oh, the letters are in weird order. Sorry, guys. You see it's like 0 through 15, and then it's, or 0 through 14. They're supposed to be next to each other, but like my page didn't hold it in very well. Should be something like this, but it does kind of fit. Okay, I just didn't like how it fit. So you can go down this way. Anyway, if I was to give you a piece of paper and it said 8, 9 with a winky face. I mean, if you figured out that the numbers somehow went to letters, you probably would pretty quickly decipher that message. If I was to give you a paragraph of text, and the numbers only went from 0 to 26, and certain numbers were repeated a lot, like the number 5, or like the number 19, you could probably guess, I think 5 are E's, and I think 19s are S's, and I'm going to use that in order to go back and figure out what the coded message is. So even if I started doing tricky things, like only using odd numbers or only using even numbers, if you looked at that paragraph of text put into numeric values and you saw things like, they're only odds, they're only evens, they're only divisible by 4, you would still see things like repeated numbers, and repeated numbers would probably go to commonly used letters. If you guys ever watched a movie called The Enigma Code, is it called The Enigma Code? But anyway, The Enigma Machine. Benedict Cumberbatch, it was out a few years ago. The Germans were using a machine to encode their messages, and it couldn't be broken, couldn't be broken, couldn't be broken, until they realized every message ended with Hail Hitler. They broke the code because they figured out what letters that had to be, and they were able to work their way backwards. Now, it was a very complicated code. Every time the machine changed, it would change the orientation. We're not going to go into all kinds of different codes. We're just going to figure out how matrices can encode. So let me give you an example. I know you guys might not have gotten all of this written down, but I want to give you an example. Here we go. Of how matrices can be used. This example has been totally worked out, and if you want, you can drop your pencil. This is saved in the notes. They'll be on the video. I want to show you how a message can be encoded with a matrix in a very complicated, hard to decipher kind of way, and then how that very same matrix's inverse can be used to decode. Do you guys see how I've broken up this message into pairs of 2? Help is on the way. Okay. Using the spaces as well. I broke it up in 2s because my encoding matrix, whose determinant can't be 0, by the way. If its determinant is 0, there's no inverse, there is no undoing, there is no going back. If you send a message that's encoded, you probably want the person getting it to be able to decode it. So, an encoding matrix, a 2 by 2, split up into 2s. I took each letter, and what did I do with each letter? Pause. What did I do? I made them into numbers. I took all of those rows, and what did I make down here? A long matrix. My whole message is right here. Do you see it? Help is on the way. Help is on with spaces is on the way. But these zeros are spaces and numbers are repeated that are common letters, etc. But what did I do to my message? I encoded it. I put it through the matrix. And now all of a sudden I have negatives, I have positives, I have bigger than 26, I have letters that aren't repeated. Don't die. You can take a message to numbers, multiply it by a matrix, and all of a sudden this message is crazy hard to decode unless, splitting up into 2s, unless you have the inverse. And then you get back to the original message. All right, cool kids, play with section 8.5. This is on the notes if you want to use how to go from a coded message to an uncoded, or an uncoded to a coded. Have your calculators this weekend or you'll be very sad. Bye, guys.